my calculus doing friends. We've been doing solids of revolution, and now we're going to do 5.3. We had talked about the fact that there is 3 different methods of finding the volume of these solids, and we had done 2 of them in 5.2, and they were similar to one another, the 2 that we did, the disc and the washer. In the disc, what you did is that you sliced a figure like that. This is a candlestick, and so anyway, so you sliced a figure like this, slice, and each one of those slices looked like a disc. And if it had a hole in it, then it was a washer, and was similar though, but you found the volume of each disc and you used the integral to add them all together. We're going to do something different. We're going to be finding the volume of things that look exactly like the same shape, and so that's not what's going to be different. What's going to be different, so they're going to be circular, and I have to use my toilet paper. This toilet paper is precious, you know, in this time. But instead of slicing it like this, slice, and again, having all those discs, and in this case they would be washers because this is hollow, but instead I'm going to pill it, is what I'm going to do. And so when I get to here, am I pilling it? You would cut this, but this is precious and I can't be cutting this, right? And so you can find the volume of this, and so you can simply find the volume because it's a rectangle by length times width, right? And then the thickness. And of course, we're going to try to have it wafer thin. And then what you would do is you would peel the next piece off. And theoretically, and you guys have used toilet paper before, all-purpose paper as they call it in Boy Scouts, but theoretically these pieces should be getting a wee bit shorter than each other as I go in. Do you guys agree? I mean, there should be a little bit smaller, and they certainly are, and so you're going to find the volume of each one of them anyway. So that's the idea. So the idea here is then that the volume is going to equal the width times the height, or the length times the width, whatever you want to call it, times the thickness. I didn't leave myself enough room to write thickness, right? And that thickness is what we're trying to make go to 0. But I want to show you something. Remember how this was round? And so remember how it was round, and then I pulled it out like this. And so what I'm calling the height is this right here. I'm calling this here the height, how tall it is, and because it's kind of standing up here like this. And do you guys realize that what the width is? The width, this width right here, is when it was a circle. You don't call it W, you called it circumference, right? So that width, the width is the circumference, and circumference equals 2 pi r. And so what this is going to be then is the width, 2 pi r, times the height, times the thickness. So that's going to be kind of our story. So here is our basic method, our basic technique of finding it, and then we'll practice some, and then we'll compare and contrast in the next video on 5.3. And so I'm kind of going to break 5.3 into 2 videos. Okay, so basic technique for finding the volume of revolution. It matters if you're going around the y-axis or something parallel to the y-axis. If you are, then your equations must be solved for y. The graph of your equation, you want to graph it out, what's going to be revolved, and sketch it. And you want to, when you're doing the shell method, I forgot to say that was called the shell method. The reason that it's a shell is because it's like when you start peeling these off, you're peeling off the outer shell, and kind of like peeling an onion. And so anyway, so this is called the shell method, and so you want to identify the typical H. And I said, note that H is parallel to the axis of rotation. And so often H equals top curve, I wrote bottom, top curve minus bottom curve, often. And so we'll look at that. And then you're going to draw your typical radius. And your radius is perpendicular to the axis of rotation, and so we'll label what our R value is. And so the radius goes from the axis of rotation, in this particular R, from the axis of rotation out to H is where it's going to go to. It's the distance from the axis of the rotation to H. Okay, and so then your volume will look like this. The integral of 2 pi r times h dx, there's your thickness, right? So all of our pieces from A to B. And if you're going around the x-axis, all the opposite story. And here our h is going to be typically right curve minus left curve. And we'll look at that. And then your R goes from the axis of rotation to H, and then this is what it's going to look like. So, and we're going to be writing these out each time so that you can see how it would go. If you're wanting more examples and you want a guy that's got a pretty snazzy way of doing it and whatnot, you can go watch Professor Rob Bob, and here is his a link that used to be good. I hope it's still good. I should check that out. Okay, so this is one from your textbook. I got this going from your textbook so that I could so that I can show you what the solid looks like and whatnot. And unfortunately, didn't remember that I had that there. So now I'm having to get it on my computer so that I can show you on here. Let's see here. So I have to just concentrate, otherwise I won't be able to do it very fast. You're already going, oh my gosh, I'm giving this one a thumbs down. Oh, my flash drive's not even in there. Did I leave it at school? Okay,